Hi everyone, today we are going to focus on transportation problems, on how they are modeled and solved using linear programs and Microsoft Excel. Transportation problems in general are problems that involve transporting items or equipment across various paths. So we may have flow constraints moving from point A to point B. We'll have multiple points interconnected, and we'll normally have a source or starting point of those resources, as well as a sink or a goal location that we are seeking out. So the easiest way to get into these is just go through an example. So let's start with our Midwest Electric example. Midwest Electric is a conglomerate supplier in New Mexico. They currently have power producing plants in the cities of Bellingham, Eugene, and Albert Lea. Okay. Each of these plants is capable of producing 35, 50, and 40 million kilowatt hours of electricity in a given day. In the same area, the towns of Sacramento, Salt Lake, Rapid City, and Albuquerque, they have an electrical requirement that must be met on a daily basis of 45, 20, 30, and 30 million kilowatt hours of electricity, respectively. Since new laws have recently been passed allowing citizens in different areas to choose their electric provider, each plant is required to have the ability of serving all four towns. So that means all our providers in Bellingham, Eugene, and Albert Lea are connected to those who need electricity in these towns. Because there are different distances from each other, there are different costs associated with transporting 1 million kilowatt hours of electricity. Now note we're dealing in units of 1 million kilowatt hours of electricity here. Okay? So costs are in the table that follows. Your job is to design a daily transportation plan that minimizes the total cost of shipping electricity between towns and plants. So I'm going to zoom in here real quick. You'll see I already have this table built out for us. We have a nice from-to matrix here. We're going from these towns to these towns. So really we're going to start right here, and the thing we're going to do first in this case is we are going to copy and paste. We are going to delete the insides. We are going to change these so they are numbers. We are going to format these cells so that they have no background, no fill value, and they have a different color border. Those are red, and that's right. That means these are our decisions we are going to make, right? Because what we are planning to do here is saying, how can we minimize the cost of power supply transportation while meeting all demands, fair, by choosing how much generated power to send to each location. Fun thing with these problems, we'll take up the amount used, right, and the demand, or you could even say the amount received here. Okay? These are super easy formulas. Why? Because Sacramento just gets the sum of all these values. Salt Lake City gets the sum. Albuquerque gets the sum. And this is the same here. How much power did Bellingham produce? Well, it's the sum of the amount sent to each one of those. Great. So we now have some constraints, right? Each of these plants is capable of producing 35, 50, and 40 million kilowatt hours. So we are going to say we have some supply here. We'll put these in kWh. And we will put that in the proper location. And we know what these are. These are 35, 50, and 40. These are constraints, but we'll get to that in a minute. And we know that our inequality here, since this is a supply and we can't use more than our supply, we can only produce as much as we are capable of producing. So that gives me a less than or equal to. We also know that each city has a demand in kWh, actually millions of kWh, but we're going to say kWh here. That demand is 45, 20, 30, and 30. Since we must meet demand, meet or beat it, we know that these are greater than or equal to constraints. These are all constraints we have. So we are going to go ahead and fill those appropriately. We're going to give them our nice blue border. Going to give them our nice gray fill. Okay, and we know our goal here is to minimize our shipping cost. This is going to be our nice objective cell. We'll give it that nice double border. Great. And what we'll do is we'll take the sum product of all of these costs, with the sum product of the amount that we have to send to each city. Okay, and you'll note this is a really nice setup now because I have all of these things in a nice matrix form. I can use my sum products and my sums. And once this is done, go ahead and save it for safety's sake. Jump into Solver. If you have data in there, just go ahead and clear it all out, reset all. We are going to minimize by changing all of these cells. We are going to add constraints. My amount used must be less than or equal to my constraints. My amount received must be greater than or equal to my demand. Make them non-negative, use the simplex, and solve. Let's see what Solver can come up with. There we go. There's my shipping cost. There is everything going in there. Okay, so this is real easy. It's telling me how many units of electricity to ship between all of these. So for instance, I'd be shipping 45 million kilowatt hours from Eugene to Sacramento. Okay? This is really nice. This is a really clean formulation. But I also want to show you an alternate formulation for this same problem that perhaps gives you more of a sense of flow. This is very clean, very clear. I think it's very straightforward. What we're going to do is we're going to do the same thing. We're going to start from this position here. We're going to go to our next spreadsheet for our alternative. I'm going to zoom in a bit here so we can actually see what's going on. And we are going to start by making some different choices. Okay? We are going to number all of our from and to. So we are going to number these as source 1, 2, and 3. So these are now all sources. Okay? We have this nice source here. 1, 2, 3, 4. These are also my destination, right? So I have destinations and I have sources. Okay? So what we're going to do, and fundamentally what changes this problem, is that we are going to formulate our decision variables a different way. And the way we're going to do that is we are going to start with our origin, and we're going to go to our destination. So I know that origin 1, or source 1, can go to destination 1, 2, 3, or 4. I also know that origin 2 can go to 1, 2, 3, or 4. And I know that origin 3 can go to 1, 2, 3, or 4. We're going to go ahead and fill this all out. And if you didn't notice, my font size is off a little bit here, so I'm going to go ahead and select my whole spreadsheet. I'm going to change this to Calibri 12. All right. There we go. So I have origin or source. I have my destination. I guess we should make these match up so that it's easy to read. Okay, so the other thing I need to get here is my unit cost. Okay, so I will have a unit cost that I have to figure out here. It's going to be 8, 6, 10, 9, right? So what I'm actually going to do here, the quickest way to do this, we're going to do a paste special. We're going to do a transpose. And we can do better than this because we can say transpose and just take my values. And we're going to do the same thing here. We're going to go to paste special, take my values, transpose. These are all dollars. And these are givens, right? Unit costs. So we should probably go ahead and put these in a nice location here. Okay? These don't all need to be bolded. There we go. So now what I get to do is pick my flow. Okay? These correspond to the same exact set of decision or changing variables that we had in the original problem. So if you come here, I'll give these a border. When I'm saying from source 1 to destination 2, that means from Bellingham to Salt Lake City. In my original formulation, that would be Bellingham to Salt Lake City. Easy, clean, clear. Okay? We can do that. The easiest way to do this then, we also have our total cost that we're minimizing. So we'll come here, we'll go ahead and format this cell. we will give it our beautiful double border. And my cost is very clear now. It is the sum product of all my prices with how much electricity I send that way. Now, the final thing that you will be thinking is, how do I add my constraints in here? This is a much different formulation. So the way we're going to do that is we're going to start and we're going to have 3 plants. Each one of those plants will have an outflow. Right? Our outflow, I'm just going to go back and copy this, has to be less than or equal to our supply. So we'll put that right there. We're going to actually do something very similar here. We're going to have our city. We're going to have 4 cities. We're going to take this Midwest alternate. We're going to paste special. As I mentioned before, transpose just flips these. Okay. This is now demand. And I must be greater than or equal to my demand. And I'm going to go ahead, I'm just going to extend this formatting very quickly. I'm going to add the fill. These do not need to be bolded, nor do these. Okay, there we go. We are now in good shape, except that I need the left-hand sides of all my constraints. Well, how much is going out from all of my plants? We are going to use a formula called SUMIF. Okay, so what we want to do is we want to look over here and say, over my sources, if the value equals 1, why then sum up the amount in my decision cells. So SUMIF says if the value in column A, A11 to A22, is equal to 1, G11, then sum up the corresponding value in D11 through D22. Now you can see that this works. If I put a 1 here, that'll sum up. If I put a 1 here, it doesn't add anything. Okay, this is pretty nifty. If we did that all correctly, we should just be able to drag it down, and you'll see if A11 through A22 is equal to 3, or G13, sum up the corresponding value. Now we are going to be a little slick here because I don't want to do as much work. The outflow is just the amount going into a city, so all we have to change is my destination. What that says, and you'll see this is the same here, so for instance in here it says look at B11 through B22, my destination, see how much is being sent into it, or match it with the city I'm looking at, and then sum up how much is being sent to it, D11 through D22. Okay. So we can come in here, we can go to solver, we can say we are minimizing this by changing these cells. We can add these are less than or equal to this, and we can also say our outflow is greater than or equal to demand. Now hopefully you saw something here. I'm going to change this to simplex. I'm going to close this real quick because this should be inflow, not outflow. I made a mistake in my model. We'll go back to solver. Everything is still there. I'm minimizing my cost based on this. So let's solve it and see what happens. Hey, same result, same answers. 2 formulations to the same problem. Why may I want to do one formulation over another? Well, they're 2 different representations, 2 different models. This representation represents the flow across a graph very clearly. In mathematics and in simulation, we would talk about source and sink nodes, where each city or each destination or each pit stop is a sink, or not a sink, a node in the middle, an intermediate node. And we would generate things at the source, our power plants in this case, and we would receive them at the sinks or destinations, which are our cities at this point. So it's just a matter of context. Which one is cleaner, which one suits your model better, and which one you are able to use the best. So there is our first example of transportation problems, 2 different model formulations.